Good morning, laser nerds, and welcome to Photonics Frontiers, where we discover the latest and greatest in photonics together. So, the race to replace some point. In the last 18 months, we've seen breakthroughs landing faster than most roadmaps predicted. All optical chips beating top NVIDIA GPUs by roughly 100 times on the workloads that they were measured against. There's a race. There's a full on race for this. This is the future of computing arriving ahead of schedule. So let's break down the 12 technologies pushing photonic computing to its absolute limits. Number one, we have LightGen, the all-optical generative AI chip. Researchers at Jiao Shanghai Jiao Tong University, help me, Giga Chan, working with Tsinghua, built the world's first fully optical generative AI chip, LightGen. 2 million photonic neurons in a 3D stacked architecture with no electronics in the compute path at all. It handles image synthesis, style transfer, video manipulation, and denoising entirely in the optical domain. The headline number, roughly 100 times faster and 100 times more energy efficient than NVIDIA's best electronic chips on the image synthesis benchmarks that they ran. This is one of the most concrete demonstrations to date that optical computing isn't just viable for AI, it's pretty superior for specific workloads. Number two, light matter passage. Light matter passage, M1000. Somebody correct me on that. This is a photonic super chip that light matter is producing. So they dropped Passage M1000, which is a 4,000 square millimeter photonic interposer that connects up to 34 chiplets on a single optical substrate. 114 terabits per second of bidirectional bandwidth, 1,024 high-speed SerDes lanes, 256 optical fibers, and the world's first built-in solid-state optical circuit switching. Manufactured by Global Foundries and Amkor, this isn't a processor, it's a photonic nervous system for AI data centers. It eliminates the electronic interconnect bottleneck entirely, letting thousands of GPUs communicate at the speed of light within a single domain. Per light matter, it's the fastest AI interconnect ever announced. Number three, Purdue's single photon optical switch. Purdue may have built the long missing primitive for an all optic logic gate, a photonic transistor that operates at single photon intensities. A single control photon triggers a carrier avalanche of up to 1 million electrons in silicon, which modulates a much more powerful probe beam, CMOS compatible room temperature gigahertz today with a theoretical path to terahertz. The reported non-linear refractive index is several orders of magnitude higher than any other known material. If the published numbers replicate in independent labs, this is the optical equivalent of a new transistor. Number four, Penn Engineering, AI training at light speed. Until now, photonic chips ran inference but couldn't train neural networks. The nonlinear activation functions training requires were too hard to implement optically. Penn Engineering's programmable photonic chips uses pump light to draw reprogrammable instructions directly into the material, creating nonlinear optical connections on the fly. On their benchmark, 4 nonlinear optical connections match the performance of 20 linear electronic ones. This gives us AI training in the optical domain with dramatically lower energy consumption. This is one of the first credible chip-scale demonstrations that the barrier for photonic AI can actually be cleared. Number 5, the 100 gigahertz all-optical clock. So modern CPUs tend to run around 5 gigahertz. There's some benchmarks up to 7 with like supercooling and stuff like that. Researchers at Peking University, the Chinese Academy of Sciences, and UC Santa Barbara just built an all-optical chip clocked at over 100 gigahertz. They replaced the electrical clock with an on-chip microphone, race course-shaped ring resonator where photons compete laps in billionths of a second, synchronizing every component at light speed. This is a 20 times optical improvement over the fastest electronic clocks we have. This points towards a future where the fundamental timing of computation becomes optical, not just the compute itself. Number 6, NVIDIA Spectrum X Photonics with the TSMC COUPE. So when NVIDIA goes photonic, you obviously can see where the paradigm is beginning to shift. At GTC 2025, NVIDIA unveiled Spectrum X Photonics, what they call the world's first 3D stacked silicon photonics engine for all networking built on TSMC's COUPE process. Per NVIDIA, it has 220 million transistors stacked on top of 1,000 photonic integrated circuits via 3D hybrid bonding. So 3.5 times better power efficiency and 63 times better signal integrity, bringing latency down from microseconds to nanoseconds, and 1.6 terabit per second ports designed to scale AI factories to millions. So photonics going mainstream at the biggest scale imaginable. Number 7, the 16,000 component photonic accelerator. Scale matters in photonics, and this chip obviously shattered some records. A multi-institution academic team built the largest integrated photonic accelerated accelerator ever. Over 16,000 photonics components on a single chip using 2.5D hybrid packaging to co-integrate electronics and photonics. It performs linear matrix multiply accumulate operations with 3 nanosecond per cycle latency at 1 gigahertz. For latency sensitive workloads like optimization solvers, it dramatically outperforms commercial GPUs. This is proof that photonic integration scales to the complexity needed for real deployment. Hopefully, not just demos. The Quant NPU2, technically the first commercial photonic AI processor. So this is out of Stuttgart, Germany. Quant shipped the world's first commercially available photonic native processing unit for AI, the NPU2. It's built on thin film lithium niobate on insulator with a redesigned nonlinear core that handles activation functions in a single optical step. It ships as a turnkey rack-mounted server with PCIe, full C, C++, and Python APIs. Its reported benchmarks show up to 50 times higher performance and 30 times lower energy use versus electronic processors for AI workloads. Their public roadmap projects a million-fold throughput increase by 2028. Confirming shipping status, you can buy this today, being current, would be helpful if any of you know how to do that. If it's commercially available now, this is the first photonic AI processor crossing the line from research to procurement. Number 9, the P-latch breakthrough. You can have the fastest photonic processor in the world, but if you have to convert it to electronics every time you need to read or write memory, you've already lost. USC and UW-Madison built the world's first regenerative photonic memory on a commercial foundry platform called P-latch. It combines photodiodes, microring resonators, and optical waveguides into an optical analog of SRAM. So it's fabricable today by global foundries. So the simulated speeds hit 20 gigahertz for writes and 50 to 60 gigahertz for reads. This would be roughly 20 times faster than electronic SRAM at equivalent process nodes. So the sizes they're making them now. This eliminates the conversion bottleneck that's been holding photonic processors back, and it was presented at IEDM 2025. Number 10, the electronic photonic quantum system on chip. Northern Boston University and UC Berkeley built the first quantum chip integrating photonic quantum light generation and classical electronic control on a single 1mm by 1mm die. Manufactured in Global Foundry's commercial 45 nanometer CMOS process, it produces reliable streams of entangled photon pairs with built-in feedback stabilization. The real significance is that this was actually just fabricated in a standard commercial foundry. So this puts quantum photonic systems now manufacturable at scale. Number 11, photonic ray tracing core on lithium niobate. A new entry in the didn't see this coming column. Researchers built the first photonic circuit specifically designed for ray tracing acceleration on, again, thin film lithium niobate. It performs ray box intersection tests in the optical domain and reduces analog to digital conversion in a single bit, eliminating the primary power bottleneck in analog computing. They're reporting over 100 gigahertz bandwidth at 326 femtojoules per operation. For real-time, physically realistic rendering, spatial computing, AR, VR, gaming, this would totally transform the pipeline. Graphics processing in the optical domain may show up as the next thing that we all jump on the bandwagon for. Number 12, light matter NVIs, full neural network execution in light. So they were able to demonstrate photonic computing on full state-of-the-art neural networks, ResNet, BERT transformers, convolutional networks, reinforcement learning on Atari. They executed with no model modifications and reached 6.5 trillion operations per second at 78 watts electrical and 1.6 watts optical. That performance per watt directly attacks the power wall that's starting to constrain electronic AI scaling. This being the most credible single product proof to date that photonic compute holds up to real models. This is the most credible single product proof to date that photonic compute holds up on real models. 12 breakthroughs, all optical chips matching or beating GPUs by orders of magnitude on the workloads they were built for. Photonic memory tested at 20 times the speed of SRAM. The first commercial photonic processor you can rack mount today. Quantum photonic chips rolling off the same foundry line as your phone's processor, and NVIDIA, the king of electronic compute, going all in on silicon photonics. The message here is photonic computing isn't coming, it's here. At the system level, the open questions are at the component level. Gain, endurance, foundry manufacturability, software stack maturity, and if I have a next episode, we'll go one layer down. That's the single switching element of all this is built on and why it's still being invented. See you there. Just a quick aside, I'm new to this, so if you have any corrections, comments, suggestions, please let me know. I appreciate all the help I can get. Thank you so much.